So we left off in the last video looking at this inequality where it did not have, like a standard quadratic, two real roots. It had no real roots. It does not touch the x-axis. So how do we find what values of x solve for this inequality? Well, if we look at it, we want the value of the inequality to be greater than or equal to 0. So that means touching or above the x-axis where y equals 0. So where is the inequality touching or above the x-axis? Well, that would be everywhere. It never touches the x-axis, so it's always above it. So the values of x on the x-axis here, it's the whole thing. No matter what value for x we have, the value of this expression will always be greater than or equal to 0. So the solution here is infinite. Any value for x will make this inequality true. So what we're going to see is that in these quadratics where we don't have the standard two real roots, we're going to get different types of solutions here, like this one that was infinite. But this one is not going to be infinite. It's going to be different than that. So what we can start with is this shortcut that we did in the last video of starting with the discriminant to see if there's going to be real roots or not. So for b squared minus 4ac, we will get 25 minus 4 times 4 times 3, so minus 48. Again, I just counted up the negatives. When there's an odd number of negatives being multiplied, the final number is negative. And so here we get negative 23. A negative discriminant means there are no real roots. So if we draw the graph, the parabola will not touch the x-axis. But be careful, because the leading coefficient is negative, the parabola is pointing downward. So it's going to look like this, where the entire graph is below the x-axis. So here in the inequality, we're being asked to find where is the parabola greater than 0. Where is it above the x-axis? And that is nowhere. It never goes above the x-axis. So the answer here is no solution. Okay, now we're going to take a look at an inequality with yet another type of solution that we haven't seen yet. If we do the discriminant on this one, we will get 12 squared minus 4 times 4 times 9. This is 144 minus 144. So the discriminant is 0, which means it's touching the x-axis. Because discriminant of 0 means one real root. And one real root means it can't pass through it, since that would give us two real roots. It can only touch it for one real root. It's a positive leading coefficient, so it's pointed up. So it's going to look like that. So we have one real root here, and we're being asked to find where is it less than or equal to 0. Where is the graph less than or equal to 0? Well, it never goes below the x-axis, so it's not less than 0, but it is equal to 0 right on the root. The value of the parabola is 0. So our solution here is going to be what that root is. But in order to find that root, we have to factor this expression in order to see what value of x makes y equal to 0 to give us the root. So we could factor it using the standard method when you have a leading coefficient other than 1 of draw the x and then substitute in the values as we've done before. But if you remember, there was a shortcut formula for factoring this type of problem. If you notice that the a and the c terms are both perfect squares, this is likely going to work. You just take the square root of the a term is 2, the square root of the c is 3, and we get 2x plus 3 squared. Now just make sure that works. 2x plus 3 times 2x plus 3. This is the formula we're using here, in case you forgot. This would be 4x squared plus 2 times 2x plus 3 is plus 12x. Plus 3 squared is 9. So it works. So this is the factored form of this expression. What value of x is going to make it equal to 0? That would be x of negative 3 over 2. And that is our solution here. Negative 3 over 2 is the only value for x that makes this inequality true, because it's never less than 0. We basically just turned it into an equal sign. Where is it equal to 0? And that would be at the root of negative 3 over 2. Now notice here that we once again have where this special factoring pattern is going to work, because we have square root of 9 is 3, square root of 16 is 4. They're both perfect squares. We can do the discriminant just to confirm that. Actually, 24 squared is going to be a high number, so perhaps we will skip that. But if we had done the discriminant first here, proving that there's only one root, this did prove that this factoring pattern would work, because this factoring pattern works when we have one term being squared, which produces only one root. So it all ties together. When discriminant is 0, there's one root. When there's one root, it factors into this kind of expression using this formula. Anyway, so in this one, if we assume that this formula is going to work, well, actually, the first thing we will do is factor out a negative from the whole thing to just make it easier. And so if we assume the formula is going to work, we take the square root of 9 and square root of 16, so we get negative 3x plus 4. Sorry, 3x minus 4. When there's a minus here, there's a minus there. Squared, and don't forget to bring over the negative there. Actually, it doesn't really matter for this problem, but I still want to keep it there, just to be correct with everything. And so the root of this parabola, if we were to set it equal to 0, let's just show that, the root is going to be 4 over 3. That's where the parabola is equal to 0. Because it's a negative leading coefficient, the parabola is pointed downward, and it touches once at the root of 4 over 3, right there. But what we want to know is, where is it greater than 0? Where is the inequality, the parabola, greater than the x-axis? And that is nowhere, because it only touches the x-axis. It never goes above it. So there is no solution here. So for this one, once again, we have a negative coefficient of x squared, so we can just factor that out, and this is going to make everything turn positive. And you should be able to pretty clearly see here that the way to factor this best would not be to do this method with such high numbers. It's to notice that 25 and 49 are perfect squares. So square root of 5 is 25 is 5, square root of 49 is 7, so we get 5x plus 7 squared. Actually, it is important to keep the negative here to remind yourself that a negative leading coefficient makes the parabola point downward. And here we want to know where along this parabola is it less than 0, so below the x-axis. Well, you might say, well, it looks like it's below the x-axis everywhere. But don't forget, not right here at the root where it touches the x-axis. At that point, it is equal to 0, not less than 0. So it is less than 0 everywhere except the root. So in order to find out the answer, we need to figure out what is the root where it's not equal to 0. From this factored form, we can see that it is negative 7 over 5. So what we can do, if we treat this x-axis sort of like a number line, is put an open circle around the root of negative 7 over 5 to show that that does not work for this inequality. But anywhere less than that value works, and anywhere greater than that value works. So if it's all solutions except for negative 7 over 5, we can write that in an inequality form by saying x is less than negative 7 over 5 or greater than negative 7 over 5. And with that, I believe we are done with this video. So in the next video, we will come to the conclusion of our rather long unit on graphing quadratics with our last video on quadratic inequalities.